Hi children, we continue with the fifth chapter, periodic classification of elements, and our today's topic is trends in the modern periodic table. Trends in the modern periodic table means we will be discussing certain properties of elements, and then we will see what happens to these properties when we move down a group from top to bottom of a group and across a period, from left to right in a period, what happens to these properties. That is what is meant by trends in the modern periodic table. The first property that we are going to discuss is valency. The first property that we are going to discuss is valency. What do you mean by valency? Valency is the number of electrons. This is the combining capacity of an atom of an element. That is the simplest definition of valency. It is the combining capacity of an atom of an element. Why do atoms combine? Atoms combine with other atoms to get the configuration of the nearest noble gases. Noble gases are considered to be the stable atoms. Noble gases are considered to have the most stable atoms, most stable electronic configuration. So, all other atoms try to attain the configuration, electronic configuration of the nearest noble gases. In that attempt, atoms gain electrons, lose electron or share electron with other atoms. So, the number of electrons gained, shared or lost in order to attain the configuration of the nearest noble gas, that is known as valency. So, valency is the combining capacity of an atom of an element. Atoms combine in order to get the stable electronic configuration of the nearest noble gas. In search of stability, they combine with other atoms. In that attempt, they can share electron, lose electron or gain electron. The number of electrons gained, lost or shared in order to get the configuration of the nearest noble gas is known as valency. For metals, we will see what is the valency of metals. Metals generally have 1, 2 or 3 valence electrons. Metals have 1, 2 or 3 valence electrons. So, what is their general tendency? For example, sodium configuration is 281, magnesium it is 282, aluminum we will write 283. All these are metals. So, they generally, metals have 1, 2 or 3 valence electron. So, what will be their general tendency? How can the sodium attain stability? If it is losing this 1 electron, it will get the configuration. Now, it will get the configuration of neon. So, what is its valency? 1. What is the valency of magnesium? If it loses 2 electron, it will get the configuration of neon. So, its valency is 2. Aluminum, the same way, aluminum can attain stability by losing 3 electrons. So, its valency is 3. So, generally metals have 1, 2 or 3 valence electron. So, their general tendency is to lose these electrons, thus attaining stability. Losing electrons in the valence shell to attain stability. So, generally their valency is 1, 2 or 3. So, metals generally have 1, 2 or 3 valence electrons. So, their general tendency is to lose these valence electron in order to get the configuration of nearest noble gases. So, their generally their valency is 1, 2 or 3. Or we can write for metals, valency is equal to the number of valence electron, isn't it? Sodium has 1 electron in the valence shell. So, 1 valence electron, valency is also 1. Magnesium, 2 valence electron, valency is also 2. Aluminum, 3 valence electron, valency is also 3. So, for metals generally we can write their valency is equal to the number of valence electron. Generally metals valency is equal to number of valence electrons. Now, for non-metals generally have 5, 6 or 7 valence electrons. Non-metals generally have 5, 6 or 7 valence electrons. So, what is their general tendency? For example, let us write nitrogen. 2,5. It's a non-metal with 2,5 configuration. So what is the tendency? How can this nitrogen attain stability? It has to gain 3 electron, isn't it? It has to gain 3 electron, then its configuration will become that of neon, 2,8. So, then oxygen, 2,6. How can it attain stability? By gaining 2 electrons, so that its configuration becomes 2,8, that of neon. So, generally non-metals have 5, 6 or 7 valence electrons. So, what is the general tendency? They will have a tendency to gain electron, 5, 6 or 7 valence electron. So, the general tendency will be to gain 3, 2 or 1 valence electron. Here 3 electrons are gained. For oxygen 2 electrons are gained. One more I will write, fluorine. 2,7 configuration. It has to gain 1 electron to get the configuration of neon. So, the general tendency is to gain 3, 2 or 1 electron to get the configuration of the nearest noble gases. Okay, so how can we write it for non-metals? For non-metals, valency is equal to 8 minus number of valence electrons. For nitrogen, how can you write it? 8 minus, what is the number of valence electron for nitrogen? 2, 5. 8 minus 5, making it 3. For oxygen, 8 minus, number of valence electron is 6, making the valency 2. Then fluorine, 8 minus 7, 1. Valency of fluorine is 1. So, for non-metals, valency is equal to 8 minus number of valence electron. Is it clear to you? So, metals generally have 1, 2 or 3 valence electron. So, their general tendency is to lose these electron and get the configuration of the nearest noble gas. So, number of valency is equal to number of valence electron. But for non-metals, they have 5, 6 or 7 valence electrons. So, their general tendency is to lose electron, gain 3, 2 or 1 electron to get the configuration of the nearest noble gases. So, we can see that 8 minus number of valency is equal to 8 minus the number of valence electron. Okay, for non-metals. Now, actually our topic is trends in the modern periodic table. What happens to valency across a period and down a group? What happens to valency when we move from left to right in a period? So, this is period number 3. I have written elements in period number 3. Sodium, magnesium, aluminum, silicon, phosphorus. These are the elements of third period. You can check it with your periodic table in your textbook. Okay, their atomic numbers are written. Sodium with atomic number 11, magnesium 12, aluminum 13, argon ending with argon 18. So, let us write the configurations of these elements here. Sodium it is 281, magnesium it is 282, aluminum 283, 285, 286, 287, 288. Now, shall we write the valencies? What is the valency of sodium? It has configuration 281. How can it attain stability? By losing 1 electron. So, valency is 1. Magnesium has to lose 2 electrons to get the configuration of neon. So, valency is 2. Aluminum has to lose 3 electrons to get the valency of neon. So, it is 3. Now, look at silicon. Silicon is a non-metal with 4 electrons in the valence shell. Same is the case with carbon also. 4 electrons in the valence shell. So, their gaining and losing is not possible. What they do? They share 4 electrons. Anyway, number is 4. So, valency 4. They can either lose 4 electron or gain 4 electron to get the configuration. If it is losing 4 electron, it will get the configuration of neon. If it is gaining 4 electron, it will get the configuration of argon. But it usually shares its 4 electron. Valency is 4. Now, look at phosphorus 285. How can it attain stability? Here the nearest noble gas is argon. To get 288 configuration, it has to gain 3 electron, isn't it? So, valency 3. Sulfur 286. It has to gain 2 electron to get the configuration of argon. So, its valency is 2. Then chlorine, it has 287. Needs 1 more electron. So, valency 1. What about argon? Argon is a noble gas. Its valency is 0. It is already stable. So what happens to valency as we move from, that is the trend, as we move from left to right in a period. As we move from left to right in a period, what happens to valency? We can see that valency first increases, and then decreases. Valency increases, reaches a maximum value of 4 and then decreases. So this is the trend in the modern periodic table for valency. Across a period means from left to right in a period. As you move from left to right in a period, valency first increases, reaches a maximum value of 4 and then decreases. So this is in a period. Now we will see what happens to valency when you move from top to bottom in a group, as you move down a group. In a period, it is across a period from left to right. So what happens to valency as you move down a group? Let us take the example of the first group: lithium, sodium, potassium, rubidium, cesium, francium. But we are familiar with the first 3 elements only. So we will check with these 3 elements. Lithium, it is 2, 1. Sodium, it is 2, 8, 1. Potassium, it is 2, 8, 8, 1. So what happens to valency here? All of them have 1 electron in the valence shell. So how can they attain stability? By losing this electron in the valence shell. If lithium is losing 1 electron, it will get the configuration of helium. If sodium is losing 1 electron, it will get the configuration of neon. If potassium is losing 1 electron, it will get the configuration of argon. So it has to, all these elements, they have to lose 1 electron. Same number of valence electron. So same number of electron has to be lost to get the configuration of nearest noble gas. So what is their valency? 1. So it means that in a group, valency remains same. Valency remains the same in a group. Actually, we have discussed this in the previous class. All elements of group 1 have valency 1. All elements of group 2 have valency 2. All elements of group 17 have valency 1. Like that we have learned. So all elements in the same group, they have the same valency, or we can say that valency remains the same as you move down a group. There is no change in valency. All the elements of the same group have same valency. But across a period, valency first increases and then decreases. Okay, so that's about valency. Now the next property is atomic size. Next property that we have to discuss is atomic size. So atomic size actually refers to the radius of an atom, atomic radius. Size of an atom means radius of an atom, atomic radius. It is the distance between center of the nucleus. Size of an atomic size or atomic radius is equal to the distance between the center of the nucleus, and the outermost shell of an atom. The distance, atomic size refers to the radius of an atom. It is the distance between the center of the nucleus to the outermost shell of an atom. Okay, distance between the center of the nucleus and the outermost shell of an atom. Now let's see what happens to atomic radius as you move down a group. In a group, as you move down, what happens to atomic radius? So here what happens? In a group, you can see that as you move down, lithium, sodium, potassium, etc. Lithium has 2,1 configuration, sodium has 2,8,1 configuration, potassium has 2,8,8,1 configuration. So I will draw the atomic structure of lithium. So this is the nucleus. How many shells are there? K shell is there and L shell. K shell there are 2 electrons. L shell there is 1 electron. So for lithium, what is the atomic radius from the center of the nucleus to the outermost shell? This is the atomic radius for lithium. Distance between the nucleus to outermost shell. Now I will draw the structure for sodium. Nucleus. This is the nucleus. How many shells are there for sodium? 1, 2, One more shell is there, isn't it? Sorry. Lithium it is. I will draw it for lithium. Lithium, this is the nucleus. K shell, L shell. 2 electrons in the K shell, 1 electron in the L shell. Now so this is for lithium. Coming to sodium. Nucleus, K shell, L shell, one more shell is there, L shell, M shell. So K shell there are 2 electrons, in the L shell there are 8 electrons, and in the M shell there is 1 electron. So here what is the atomic radius distance between the center of the nucleus and outermost shell? Lithium it is. This is the atomic radius. Which one has higher atomic radius? Sodium. Why? What is the reason for that? In sodium, as you move down the group, lithium has only 2 shells. Sodium has 3 shells. When you come to potassium, it has 4 shells. So, distance between the center of the nucleus and outermost shell increases as the number of shells increases. Okay. So, as you move down the group, atomic radius increases. Atomic radius increases down the group, because as you move down the group, new shells are added. Lithium it is 2,1, sodium it is 2,8,1. When it comes to potassium, 2,8,8,1. So distance between the nucleus and the outermost shell will be more in potassium. So as you move down, the size increases, atomic size increases. So as you move down the group, the biggest size for the atom will be the last one, the last element of that group will have the maximum size. Now we will see what happens to atomic size as we move from left to right in a period. As you move from left to right in a period, we have discussed the elements of the third period: sodium, magnesium, aluminum, like that we have discussed. Then what happens? 281, 282, 283, like that it goes on. Under valency we have seen this elements of the third period. So you can see that there is no increase in the number of shells. As you move from left to right in a period, there is no increase in the number of shells. Electrons are added in the same shell. Then what happens to atomic size? Do you say that the atomic size remains the same? No, it is not like that. When you move from left to right, atomic size actually decreases. This period will end with argon. 288. So you can see that everywhere in all the elements, electrons are added in the third shell. There is no increase in the number of shells. But atomic size decreases because as you move from sodium to magnesium, nuclear charge is increasing, electron is increasing, at the same time number of proton. This one has 11 proton, here it is 12 proton, 13 proton, like that. The charge of the nucleus is increasing, or the power of the nucleus increases. So nucleus will be having a tendency to pull the outermost electron closer towards it. Electrons in the outermost shell will be pulled closer towards the nucleus as you move from left to right. Nuclear charge, power of the nucleus increases. So this nucleus tries to pull the outermost shell more closer towards it. Negative charges will be pulled closer towards this nucleus. So what happens as a result? Size decreases. So as you move from left to right in a period, atomic size decreases. Okay, so this is the trend of atomic size. Atomic size actually refers to the radius of an atom. It is the distance between center of the nucleus and outermost shell of an atom. In a period, in a group, as you move from top to bottom in a group, number of shells increases. As you move down the group, you can see that as you move down, number of shells, each element will be having one more extra shell. So number of shells increases. So the distance between the center of the nucleus and the outermost shell increases. So atomic size also increases. But across a period, electrons are added in the same shell. As you move from left to right in a period, electrons are added in the same shell. But as you move from left to right, nuclear charge increases. Nuclear charge increases, or the power of the nucleus increases. So this nucleus will be having a tendency to pull the outermost electron more closer towards it. Thereby, the size of the, by shrinking the size of the atom decreases. As you move from left to right, size of the atom decreases. So here, this is the third period. Here, as you move from left to right, size decreases. So this will be the smallest atom. Argon will have the smallest size and sodium will have the biggest size in third period. Okay, as you move from left to right, size decreases. So that's all. Thank you, children.